In this video, we will discuss limits at infinity. And let's consider the graph of the function f of x given below and use this as motivation. What I would like to answer is the question, what happens to the function f of x as x gets larger and larger? Well, looking at the graph and thinking about, plugging in large inputs of x, assuming the function has the same behavior we see, it looks like those outputs are getting really close to 2. And what we will say is that the limit as x approaches infinity of a function is the number L if the outputs of the function f of x become close to L as the inputs x get larger and larger without bound. So saying x approaches infinity means that as we plug in larger and larger values for x, the outputs are approaching some fixed constant L. So in the example above, we have that the limit as x approaches infinity of this function is the number 2. And note, if you recall from maybe a previous pre-calculus type course, this is equivalent to saying that the horizontal asymptote is the line, in this case y equals L, or in the above example it would be the line y equals 2. So let's consider the following limit as x approaches infinity of 2x cubed over 1 plus x cubed. And it turns out that this is a very common type of limit, and there's a technique that allows us to evaluate this quickly and efficiently. When it is a limit of a rational function, as you approach plus or minus infinity, the technique is as follows. You divide the top and the bottom by the largest power of x that appears in the denominator. So looking at our function here, the largest power of x that appears in the denominator would be the x cubed term. So what we are going to do is multiply by 1 in the fancy way. 1 over x cubed divided by 1 over x cubed. So now we'll have the limit as x approaches infinity, and in the top 2x cubed over x cubed is 2, and in the bottom when we distribute the 1 over x cubed through, we end up with 1 over x cubed plus 1. And we can now apply our limit laws. We take the limit in the top, divide it by the limit in the bottom. But for the limit in the bottom, we'll have the limit of the first plus the limit of the second. Now, 2 of these limits are quite efficient for us to evaluate. The limit of a constant is simply that constant. For the limit as x approaches infinity of 1 over x cubed, well, let's just note as long as, let's say, n is a positive number, the limit as x approaches infinity of 1 over x to the n is going to be 0. Because as x goes to infinity, that x to the n is going to become really large, and 1 divided by something really big is a 0. So the first limit in the bottom is also a 0. So we end up with 2 over 1, which is the number 2. And once again, the big picture observation, when evaluating the limit as x approaches plus or minus infinity of a rational function, the technique is to find the largest power of x in the bottom and multiply by 1 over x to that power divided by 1 over x to that power. So you're essentially just multiplying by 1 in a fancy way, which does not change the value of the limit. So a very similar approach. It's a limit as x approaches infinity of a rational function. So we look for that largest power of x in the bottom, so in this case x squared, and we multiply by 1 over x to that power divided by 1 over x to that power. So multiplying by 1, and that's what we're doing here, we've multiplied by 1 in a fancy way, will not change the value of the limit. So in the top, x over x squared is 1 over x. In the bottom, when that 1 over x squared distributes through and hits each term, it will be 1 over x squared plus 1. And we can apply our limit laws. We have the limit in the top, divide it by the limit in the bottom. And the limit in the bottom can be broken up into the limit of the first plus the limit of that second function. And we can now evaluate each limit individually. As x goes to infinity in the top, 1 over x goes to 0. Additionally, in the bottom, 1 over x squared goes to 0, and the limit of a constant is that constant. So 0 over 1, which is the number 0.